I got a hot take for y'all today. I think we might have hit an AI plateau. Well, we haven't hit it yet, but I think we're getting there fast. What do I mean? This can't be possible, right? When we look at all the new models and all the crazy things you can do with them, the improvements from ChatGPT 2 to 3 to 3.5 to 4, with Claude coming out of nowhere and being really good, with open source models like Llama and Mistral, we can't be at a plateau. That's crazy, right? Well, there's a lot of things that have these patterns, and I want to start with a bit of an interesting tangent. I want to talk about Moore's Law. If you're not familiar, Moore's Law is an old concept from the programming world. It's a law created, or it's not a real law. It was some speculation from a dev and a hardware enthusiast back in the 70s. And he noticed how fast things were improving in terms of performance. His observation is that the number of transistors on a microchip roughly doubles every 2 years, and the cost is halved over the same time frame. So if you had a chip, let's say, that had 4 transistors on it, within 2 years, with advancements on how we were manufacturing these chips, we'd get it up to 8 transistors, and it would be cheaper. And we did that over and over again and saw massive growth in performance of our machines. It was actually realistic for a bit. If you took a computer that you went and bought at Best Buy and then waited 2 to 4 years, bought a new one, the processor could be 2 times faster in a very short window. And it's crazy to think because now, if you buy an Apple M1 computer from 2020 and a brand new top of the line machine from 2024, the performance difference between those things is not that big. But back in the day, we saw insane improvements year over year. We've started to hit walls with the physics, though. We realized you can only get so small for the silicon before you start running into manufacturing problems. Now the manufacturing processes for a lot of these things are so complex, there's only 1 or 2 companies that can even do it at the small sizes that we're expected to hit now. If you want to make the most efficient chips possible that fit as many transistors into your die as possible, you have to do that through a company like TSMC, because they're one of the only places in the world that can manufacture that way. And companies like Intel, Apple, and NVIDIA all rely on that one manufacturer, TSMC, that is still not hitting the Moore's Law goals, but they're the only ones even vaguely close. We've effectively accepted that Moore's Law, due to physics, is no longer true. Here we see from a study where somebody proposed a new alternative to Moore's Law. The blue line is Moore's Law, the orange line is their alternative law, but the green is performance. And you'll notice things are flatlining pretty hard up here when before they were going up at a relatively steady rate. From the 70s to the 2000s, even to 2015, things were going up pretty steadily. But we've started to see a flat line. And the harsh reality is that from 2020 onwards, it's gotten worse, not better. That's terrifying. Obviously, there are companies that disagree. Here is a diagram from NVIDIA where they actually admit that the CPU performance we're seeing has plateaued pretty hard, where we went from getting multiple giant wins to around 1.5x per year, down to 1.1x per year. I'm streaming right now using a PC with hardware from, when did the 10700K release date? Yeah, the processor on my desktop's from 2020. It's not even one of the high-end ones. It doesn't perform much worse than the top spec one I just bought a new computer in a different room. Performance wins year over year have gotten way worse. Even though the technology is still advancing, we're still making big wins in the manufacturing. Intel and AMD are as competitive as ever. We're still not seeing massive wins anymore. This does have benefits though. If you buy an old processor for way cheaper, you still get really good performance. You can buy a MacBook Air M1 from Walmart used for $400 and have great performance on a machine that I paid $2,000 for not long ago. And those things are great. I know people are bitching all about this isn't about performance as transistor count. We've used the number of transistors as a way to measure the progress of processors. And historically, if you had a big win in the manufacturing process, if you made the dies go from 10 nanometer transistors down to 4 nanometers, you would see massive wins. This is rough. Obviously, NVIDIA's doing their thing here, claiming that GPU compute performance can continue to grow. The fun thing with graphics cards is they don't have the same model with cores, with the complexity of sharing things between them, because the cores in a GPU are significantly dumber. It's a different abstraction, which means you can just staple more and more GPUs onto each other to improve performance. You might end up with a GPU no longer being a tiny little thing you slide into your computer, and now it's a giant room full of things. It's still one GPU because of the way the chips are architected. But the only way NVIDIA is going to see this type of performance wins continuously is if they just add more and more chips to their actual architecture. It's kind of cheating. But the reality is that the tech that we use today, which is traditional CPU manufacturing, we have hit a physics wall for how much improvement we can see. And the only way to get out of it, theoretically, is an entirely different architecture and way of building compute. Things that rely on this model will not benefit from these advancements as much, but anything that can work with this model could theoretically continue to see growth. On that note, GPUs are not necessarily the best way to do AI stuff. Just a quick tie-in, I think it's interesting that IBM's researching analog AI chips, similar to the stuff that we saw with Bitcoin back in the day, where before you would mine Bitcoin with a GPU, before ASICs were made, which were specialized computers just to make Bitcoin mining as efficient as possible. We're starting to see some research into doing this for AI as well, which is exciting. Potentially, GPUs aren't the right architecture for AI, and we could see advancements. And these chips, once they work, will probably advance significantly faster than CPUs or GPUs. So why am I talking about all of this when I'm talking about models? Hell, why am I even talking about models? I saw a very interesting post from Mistral. Mistral is one of the two big open source AI businesses. It's them, and funny enough, Meta. So Meta/Facebook are working on Llama, which is their open source model. It's technically not open source because you can't run the code yourself, but you get the model and you can use it however you want. Mistral is doing the same thing, and they just released Mistral Large 2, the new generation of their flagship model. Compared to its predecessor, Mistral Large 2 is significantly more capable in code gen, mathematics, and reasoning. It also has stronger multi-language stuff and function calling stuff. Cool. The key here is large enough. This made me start thinking a lot about the plateau that we're likely reaching. And I'm not the only one thinking about this. Here's a tweet from Jan LeCun, who is the head of AI and LLM research at Facebook and Meta. He's one of the ones most directly responsible for the creation of Llama. And he said, if you're a student interested in building the next generation of AI systems, don't work on LLMs. What? LLMs are how all of these things work. Well, let's rephrase this. If you're a student interested in building the next generation of computers, don't work on CPUs or don't work at Intel. It's obvious when you look at the numbers that iteration on CPUs is not going to be where we see massive performance wins and massive computation wins going forward. Different architectures will have to be invented and iterated on for us to see meaningful improvements in performance year over year. Apple does this in all sorts of interesting ways. One of the crazy things Apple invented was the idea of having different cores with different roles. So you had efficiency cores that are trying to use as little power as possible to do simple things, and then performance cores that use way more power but are quite a bit more powerful. They also started embedding things like video processing and video encoding chips that just do H.264 or H.265 decoding and encoding way more efficiently. Apple started adding things to their processors that weren't just CPUs and also weren't just GPUs in order to optimize specific things so they could keep seeing massive performance wins. I think this is the future for AI as well. And I have a reason. I have a very similar chart to this one. Notice how much smaller the wins are getting. Claude saw another solid one with Sonnet in 3.5, but the gap from GPT-4 Turbo to Turbo 2 to 4.0 is a lot smaller than from 4 Turbo to 4. It is way smaller than from 4 to 3. Claude 1 to 2 to 3 saw massive wins, but those are starting to slow down as well. We're seeing a plateau of the quality of the responses these models are generating. It is not like going from 4 to 4 Turbo to 4.0 was less work than going from 3.5 to 4. If anything, there is more money, more time, more GPUs, more effort going into these bumps. And the actual bump we're seeing is going down. So each of these iterations takes more money, more time, more compute, more energy, and the results are not as big as they used to be. I know a lot of people are saying the AI future is going to doom us all because the AIs keep getting so much smarter. Eventually, they're going to be smarter than all of us. I don't see that here. I don't see that here at all. What I see is a theoretical ceiling that we're getting very close to and a closing of the gap in performance between these different models. More and more, these options are going to become commodities. The same way you have like 15 different computer manufacturers making the same Windows laptop that has roughly the exact same performance, we're starting to see that here too. I have to read a LinkedIn post, which I know, pain, cringe, miserable. So I'm going to soften the blow with an XKCD first. This one was linked in chat and I thought it was really funny. Number of computers created is going up a lot year over year. In fact, I think it's going up exponentially. But the number destroyed by hurling them into Jupiter is a much smaller number. It's only 3 so far. NASA needs to pick up the pace if they ever want to finish the job. Yeah, they ever want to catch up, they got work to do. It's a fun way to think about data in these ways the compute changes over time. Anyways, the bitter lesson, famous 2019 blog post, claims that general AI methods using massive compute are the most effective. NVIDIA's soaring stock price supports the thesis, but is this approach sustainable? What are the alternatives? In the original blog post, AI pioneer Rich Sutton makes the following observations. Over the last 70 years, AI researchers have repeatedly made the same mistakes of trying to bake human knowledge into AI systems, only to be eventually outperformed by a more general method using brute force compute. This is funny because we're seeing the opposite in processors now, where processors were trying to just increase how many transistors were in them and how fast they could solve problems. And now we're seeing specialized chips being embedded in the processors that do certain things way better. Some prominent examples of what was happening before with models were custom chess and Go engines versus Deep Blue and AlphaZero. This was a fun one. The Go, not the programming language, the board game, was really hard for software developers to solve because the game has so many different potentials. You can't just encode all of them and then figure out which is optimal. And we learned after trying to make custom engines for these things that AI solutions like Deep Blue and AlphaZero that were more generic, more traditional AI, did a better job than the custom code we wrote. It took hilariously more compute to do it, like hundreds of times more, but the results were always better. The main reasons for this are the following. Building in expert knowledge is personally satisfying for the experts and often useful in the short term. It's a very good point. If you have experts that know this game really well or know video encoding really well, they can flex their knowledge, feel useful, and see an immediate result, all of which feels good. On top of that, researchers tend to think in terms of fixed availability compute when it's actually increasing daily. This is also a fair point. Yes, the amount that a given processor improves year over year has gone down, but the amount of processors you have available is going up, especially with NVIDIA going insane with their manufacturing. Sutton concludes that we should focus on general AI methods that can continue to scale, most notably search and learning. We should stop trying to bake the contents of the human mind into AI systems as they are too complex, and instead focus on finding meta methods that can capture this complexity themselves. Some of the important things that people pointed out are that Moore's law is fading, architecture of our most successful learning models were actually carefully handcrafted by humans, like transformers, convnets, LSTMs, etc. And for general computation problems, like integer factorization, progress based on human understanding was often far greater than progress according to Moore's law. Another great point. We're still optimizing algorithms in ways that we never would have imagined possible before. One that I love to cite here is the fast inverse square root, which was used in Doom in order to handle lighting, reflections, and rendering. Because knowing the inverse square root lets you know how far something is relative to multiple points, and it's used a ton for doing math in games. Previously, getting this number, getting the inverse square root, took a lot of compute. And as such, the idea of 3D games was basically impossible. But someone discovered a math hack they didn't even understand at the time. The fast inverse square root function that was in this code base had evil floating point bit level hacking. It's the comment here. This weird bit shift where they take this random hard-coded value, subtract the bit shifted long representation of y, comment, what the fuck? Next comment, first iteration where we multiply it by 3 halves and this function here, and we could run it again if we wanted to be more accurate. 3D graphics programs must perform millions of these calculations every second to simulate lighting. When code was developed in the early 90s, most floating point processing power lagged the speed of integer processing. So yeah, if you were trying to do this with floating points, which everyone was, it would eat your processor. The advantages in speed in this fast function came from treating the 32-bit floating point word as an integer, then subtracting it from a magic constant. This integer subtraction in bit shift resulted in a bit pattern which, when redefined as a floating point number, is a rough approximation of the inverse square root of that number. This function, this crazy math hack, allowed us to add dynamic lighting to 3D games. This wasn't something we got because processors were way more powerful. It was a clever hack that allowed us to invent a new genre of game effectively. Pretty nuts. Pretty crazy stuff that this enabled as much as it enabled because somebody came up with a clever math hack that's not even that accurate. It's just accurate enough. So as is said here, the wins we saw in compute, the revolution in 3D games that we saw after that code came out and people started using the engine, that wasn't because GPUs or CPUs got way better. It's because our understanding of how to use them to do these specific things got better. And we saw massive wins, not because the CPU got way faster, but because we found smarter ways to use it. And I think this is going to be true now more than ever. In the same way we're reaching the cap of how much you can do with a CPU, we're reaching the cap of how much you can do with an LLM. Companies like OpenAI show that focusing on more compute may still lead to massive gains as compute power, despite the warning of Moore's law, continues to increase several orders of magnitude over the next decades. Don't necessarily agree. Currently, the hype is definitely outperforming Moore's law. See the image below. As a result, AI is at risk of creating a deep environmental footprint, and research is increasingly restricted to large corporations that can afford to pay for the compute. It's a bitter lesson of the last year. Yeah, this is a fun one. Moore's law versus AI popularity. But again, Moore's law is plateauing, and AI is now way more popular than what Moore's law enables, so we're just spending billions on GPUs. Found a surprisingly good chart from Gartner, believe it or not. The hype cycle for artificial intelligence. Hype cycles are very common. This particular chart, the startup hype cycle, an idea happens, we have a spike of excitement. The first valley of death happens where you realize this is hard. You go hard, you go really fucking hard. You get inflated expectations, irrational exuberance, and then pain. You end up in this thing called the trough of disillusionment, where you're unsure of everything. Then the slow slope of reality as you figure out what you're actually capable of and what your product, company, vision, whatever it is, actually could resolve to. And then you hit the real company and real value. So back to the Gartner chart. It's funny because they have all these examples in here. We had first principles AI, multi-agent systems, neurosymbolic AI, more and more things happening. And we started getting into generative AI. And then we hit a massive point. Realized we needed more optimization, things like synthetic data, better model optimization, AI that is on the edge, so to speak. So it runs on our phones instead of on the servers. Knowledge graphs. But you notice we're going down because these things aren't fun. These things suck, and they're necessary for us to keep evolving. Then we started seeing AI makers and teaching kits to try and get people to actually learn shit. Autonomous vehicles, which were very painful and still are. Cars that drive themselves are far from functioning. But now we're seeing more and more things that will hopefully allow us to really benefit from AI. But we need to make sure our expectations are realistically set, not around the exponential growth every year, rather around how we apply the functionality of these things to actually benefit our lives day in and day out. I am honestly just annoyed that people pretend the models are going to get 2 times better every couple years because we went through that. That's clearly over. We're just not seeing levels up like that anymore. What I'm expecting us to see instead is massive wins in things that we're not currently using models for. Like we're starting to see video generation catch on, and it's taken us a lot of time to get there, but I could see us growing there really quickly, similar to how ChatGPT got way better really quickly. But it will also hit a plateau. And I think we're going to see more and more of those plateaus hit, and our solution isn't going to be magically make it better. It's going to be entirely different models and hybrids where we take advantage of handwritten and crafted code, maybe human massaging of things, and AIs, and intermingling and mixing those. The same way CPUs and GPUs take turns working on things, depending on what each is best at. Handwritten code and AI code doing similar stuff has a ton of potential. And I think that's going to be the future of AI. Because this is not the future of AI. This is a flat line. This is a plateau. This is us reaching the end, not the beginning. And if Mistral is saying that their model's large enough, I'm inclined to agree. Especially when you look at the numbers here and you see how close all of these models are getting to being basically even. The wins are no longer the models being way better than the others. The wins are going to be efficiency, performance, speed of responses. And then the next set of wins is going to be how we use these things in new and unique ways. This is actually a very interesting link. There's a project called the ARC Prize that was just linked from chat. AGI progress has stalled. New ideas are needed. It's a $1 million public competition to beat and open source a solution to the ARC AGI benchmark. Most AI benchmarks measure skill, but skill is not intelligence. General intelligence is the ability to efficiently acquire new skills. Challet's unbeaten 2019 abstraction and reasoning corpus for artificial general intelligence is the only formal benchmark of AGI. It's easy for humans, but it's hard for AI. Oh, this is fun. This is going to be like captions, basically. So we have these patterns, an input and an output. It's pretty clear what we do here. Configure your output grid there, and then we have to put the dark blues here, 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 and here. Submit. Fun. So the point here is these are the types of puzzles that we can intuit. Because we look at the pattern and we can learn quickly what the pattern is with these things. It looks like the light blue is ignored, red has the outward pattern, then in dark blue has the pattern with the like T shape. But AI is historically really bad at solving these types of things. So here is the ArcAGI progress. But if we look at other AI benchmarks that people use, a lot of the ones we were looking at earlier, like HelloSwag, ImageNet, all of these, it seems like things are improving at an insane rate. When you look at general intelligence through a benchmark like this, AI sucks at it. Progress towards artificial general intelligence is stalled. LLMs are trained on unimaginably vast amounts of data, yet they remain unable to adapt to simple problems they haven't been trained on or make novel inventions, no matter how basic. Strong market incentives have pushed frontier AI research to go closed source. Research attention and resources are being put towards a dead end. You can change that. I like that they call out that the consensus definition for AGI is wrong. AGI is a system that can automate the majority of economically valuable work. But in reality, AGI is a system that can efficiently acquire new skills and solve open-ended problems. Yes, that's what the general in AGI stands for. I actually fully agree with this call out. Definitions are important because we turn them into benchmarks to measure progress towards AI. I fully agree. I love that Nat Friedman is one of the advisors, the old CEO of GitHub. We also have Mike Knopp, who's an absolute legend, who's been involved in all things software dev and AI for a very long time. Yeah, I love this. And I think this is the only way we're going to really see improvements and wins with AI. LLMs are hitting their limitations. And as we saw here, they're not really winning on general benchmarks like this. And sure, we have these fancy benchmarks that everybody loves, but even these, we're starting to see a flat line and a plateau on them. We might be at the end of the LLM revolution, and if we want to see AI continue to grow and advance in its capabilities, we might have to leave behind LLMs the same way we're starting to leave behind CPUs. The future isn't an LLM, but faster. If we want the future to be AI, it has to be a different type of AI. Let me know what you guys think and tell me all the ways I'm wrong. Until next time, peace nerds.